Okay, so welcome everyone to the sixth lecture. In the first five lectures, so we have learned what are the basics in MATLAB. These are the foundational tools or the basic building blocks, you can say, to uh, write any code, computational code. So these are the basic rules. You have to be fluent with condition statement. You have to be fluent with this loop. Yeah, iterative task. You have to be fluent with writing this differential equation, how to do plots, and how to interpolation is also sometimes necessary for data analysis and so on. So based on all of this, so today I will mainly focus on some problem solving. So I will take some problem which is I mean uh, so for example we will solve a problem based on projectile motion and maybe a problem based on electric field. So problems which you have encountered during your 10 plus 2 level, or BSc level, even in so past course also. If you have physics in your past, so then you have maybe I mean at least you have heard of this problem, or you have encountered this. So so if you can solve these problems using the things that you have learned in MATLAB, so that then you will be able to gain confidence in doing the programming, and you will see what is the application of these things that you are learning in solving a real world problem. So let me start with basic problems, which is a problem of projectile motion. So let me write down, let me define the problem first. So first, so this is lecture 6. So here in this lecture we will mainly focus on solving problems, and in the end I will introduce you to the card fitting toolbox in MATLAB. So what is card fitting toolbox? So you want, suppose you have an experimental data and you want to fit it. So the fitting, you can do in, so there are dedicated software for it. Or you can do it in Origin and so on. But in MATLAB also, you can do the fitting. So and that is also quite advanced. So I will show you with given how you can use this card fitting toolbox to fit something. So for example, maybe we will talk about harmonic oscillator system. So we will take displacement data with time, and we will try to fit it with harmonic oscillator equation to extract its what is its frequency, what is its amplitude, what is the damping factor, and so on. So when you are MATLAB, when you're simulating, to know what are the parameters are. So then you are modeling it, and from so beforehand you know the parameters. Now suppose you are doing an experiment. So you have a system, real world system, and you are doing the experiment. You are looking at the experiment. Then how can you know what is the frequency, what is the damping factor, what is the amplitude? So frequency maybe from image analysis you can do, you can know, but from damping, but these are very tedious. So, but with this card fitting toolbox, if you can fit the acquired, if you can fit the data which you are getting from your experiment, so from fitting you can tell what is the damping, and what are the physical parameters corresponding to the oscillator system. So we will learn how to do that in the end. So initially we will look at different problems. So first we will focus on the problem of projectile motion. So which we have, everyone have heard of it and everyone have encountered it in their 10 plus 2 level. So problem 1 is projectile motion. So explore this with air resistance and without air resistance. So this is the first problem which we are going to, tackle today. So let me frame the problem. So suppose, you're standing here, right here, and you are throwing a ball. So a ball which is being thrown. So what will happen? And you are throwing it at an angle. So for example, this is 45 degree. You are throwing the ball, and there is some initial speed. So the speed is, let's say, 20 meter per second. And what will happen? This ball will go up, and due to the force due to gravity, so it will return to the ground. So this is the ground, and it will return. So this is a standard projectile motion. So maybe right now you are holding a pen, and you can throw the pen in the air. So ultimately it will return to the ground due to the gravity. That is also standard projectile motion. And since the air is present, so it's obviously common to uh, take the also the damping due to the air. So but let us consider first the idealized case. Let us consider that there is no damping present. So what is the equation of motion then? So you have the velocity here. So, so this is the direction with which you are throwing the ball at 20 millimeter per second. So this will have an, so if this is theta, so it will have an x component, which is, you can call it vx, which is v cos theta. And so this is v, and since it's cos theta, so okay, so let me keep it cos theta for generalization. And what will be the velocity in the y direction? So it will be v sin theta. This is how its motion will look like. So this is the initial case. Now, so what are the force that are acting on it? So if there is no damping, so then there will be only one force which is acting in this direction, which is the gravity. So what is this force? So this is mg. If m is the mass of this ball, so this is the ball, and if m is the mass, then the force acting on it will be mg, and it will be acting in the negative y direction. And also, if the air damping is present, or air drag, then what will be the force acting on it? So right, so then there will be two force in the negative y direction. One is the gravity, so which is mg, and there will be a drag force, which will also, so we know that drag force act in the opposite direction of motion. So if the ball is moving upward, so in that case the drag force will act in the negative y direction. So, so drag force will also act in this direction, and it will be something like, so consider k. Okay, so this is kVy. So the drag force will act in the negative y direction. So the minus is telling that it is acting in the negative direction. Since I am giving direction here, so I should omit this minus sign. So this is drag force. So there are two forces acting in the y direction. So now from this I can write the equation of motion corresponding to x direction and y direction. So what will be the equation of motion? Equation of motion in x direction. So equation of motion in x direction will be like this. So m dv x dt. And is there any force present in the x direction? So in x direction, in the horizontal direction, so there is no force. So if there is no drag, so then there is no force present. But if there is air drag, then in x direction also there will be this kvx. So and since the ball is moving in the x direction, so this drag force will act in the negative x direction. So this is in negative x direction, and this is in negative y direction, and this is also negative y direction. So direction of the force is a vector quantity, so its direction is also important. So this is how you can look at the forces. So these are the forces that are acting on the ball, and uh, so what is the force acting on the so these are the forces. So I mean we can write down now the equation of motion in this direction. So it will be uh, so here we have to write down the force, and that is minus k dx, because it is acting in the negative in the opposite direction of the velocity. So I can write down here dvx dt, which will be equal to minus k by m dx. So this is our one equation of motion. So I mean this is the first order differential equation. Now similarly, we can write the equation of motion in y direction. Okay, so how we can solve it? So what are the forces that are acting in y direction? So we have this drag force, which is minus k Vy, and we have the gravity, so which is minus mg. So you can write dvy dt, which is minus k by m y minus g. So this is the force. I mean, this is the equation of motion in y direction. So now, if I want to solve it, so what? How can I solve it? So basically, suppose you want to know how the velocity will look like in the as a function of time, and how the this velocity in y direction also look like as a function of time. So let me look at first in the x direction. So we know that this dvx dt. So we have this dvx dt equal to minus k by m vx. Now we know vx is basically dx dt. So we can write here d2x dt square, which is equal to minus k by m. So vx. So that is basically let me write it just vx for now. So I mean, so now if you want to solve what is the x, then it is the standard case of second order ODE. So I mean, if you want to solve it in MATLAB, then you have to decompose it into two first order ODEs. So we can write down this as dx dt equal to vx and dvx dt minus k by m dx. So this is my first two equations. Similarly, in the y direction, we can write dy dt equal to vy, and dvy dt equal to minus k by m vy minus g. So these are our four equations which you need to solve. So I mean, so now how we can solve this? So for simplicity, now rename the variable. I mean, uh, so x, vx, and y, vy. So this we can rename. So right now we are renaming this as x1, x2, x3, x4. So yesterday we are solving an second order differential equation. So we have to solve this matrix where we have two row and I mean n number of columns. So here we are what we are doing. So we are solving four first order differential equation. And so since this is a simple problem, so they are not coupled, but it may happen that there is Vy also. So I mean in that case all the equations will be coupled. So effectively you are solving you are solving parameters. You are looking at the solution in a four-dimensional phase space. So it is a four-dimensional phase space, and I mean so in that way you have to solve right now. So now you have to solve four first order differential equations, and you have to look at how they varies. I mean you so once you know what these arrays are as a function of time, Then you can plot x1 as a function of time. You can plot how velocity in the x direction changes as a function of time, how the displacement in y direction changes, and how velocity in y direction changes. Then you can also look at the trajectory. I mean, so here you can plot x1 and x2. So this is basically your x direction in displacement and velocity in x direction. So you can look at this how, I mean, it depends. And you can also use plot 3 function to include time as the z-axis. So here you have only one independent parameter, time t, and this x1 changes as a function of time, x2 changes as a function of time. So if you plot time in the z direction, so you can look at how this x1 x2, so it changes as a function of time. So I mean, we are discussing a helical kind of shape. So this kind of plot we have observed. So this, I mean, so in this way you can use this kind of function. You can use this plot 3 function to visualize a real world system. So you are throwing a ball and you want to look at how the position and the velocity that is changing, that is evolving as a function of time. And what you can do, so maybe you can, I mean, select some time. So for example, you want to look at the snapshot. So for example, uh, you want to look at what is the, okay, so I mean, you can look at the I mean, x on x2 data at fixed time interval. So maybe at t equal to 0, t equal to 2, t equal to 4, and in this way up to, I mean, so maybe at different times you can look at the section. So I mean, in nonlinear dynamics, this has a famous name. So this is known as Poker section. So, but I am not telling you in the context of harmonic oscillator systems. I mean, I am telling you what is the concept and how you can use the functions that are there in MATLAB to visualize any system. So, I mean, so that is why I have choose this simple system, because everyone is familiarized with this projectile motion of system kind of system, and once you can know how to solve a very simple, very basic system, how you can simulate it, how you can analyze it. So maybe so from the stored data, you can look at what is the maximum value, and you know what is the formula for calculating the maximum height. So you can check if that is, if your code is actually giving that value. So the basic things that you can check, and you can be sure that your code is working. So let me proceed with so let me try to simulate this equation in MATLAB. So what are the parameters that I should need? So we have to specify the system, what is our mass, what is the drag force, I mean K value, then and also you have to specify the gravity and also the time array. Now in case of projectile motion, so I mean, so there is a thing that you have to keep in mind. So I mean, what should be the time that you should choose? I mean, so you're throwing a ball and you want to simulate the trajectory, but how long you will simulate? So that is another important thing. So I mean, whenever you are also looking in case of harmonic oscillator system, so for example, its time period is let's say 10 seconds, and you are simulating for maybe up to 5 seconds. So that will not give you the desired result. And also, I mean, you have to simulate up to a certain time so that there is a steady state behavior in the system. So that is why, I mean, here also you have to know what should be the time step, what should be the time scale up to it you should simulate. So if you look at the projectile motion problem closely, so what should be the y value? So if so for simplicity, I'm assuming this that the height of this man is 0. So which is not the case, but for simplicity, let us assume, and he's throwing the ball. So the ball should not go into the ground. So that means so you will, so I mean, right now you can take, so what should be the time up to which you should solve it? So the once you get what once you know what your y value is, then you have to be sure that y is not going in the negative direction. So you can do it in two ways. So I mean, from I mean, we know what is the formula from our 12th standard, that so y value. So once you get y as a function of time, then you have to put y after a certain time. It will be 0. So it will be 0 for t equal to 0. So whenever you are starting to throw it, and also it will be 0 when it will hit the ground. So that time you can extract by setting the t to be 0. Or there is another thing. So I mean, you can try to simulate for a large time, and you will put a conditional statement that your y should not be negative. So when the y is negative, you will tell MATLAB that the values after that you should not store. So in that way, if you can, I mean, so and the mm, uh, advantage of the last method is that, I mean, you don't have to know the formula beforehand. So maybe so I mean, you simulate the system for a large time. So if, I mean, if you look at the response, so I mean, we know that its trajectory will be like this. So this is y as a function of time. So you will tell MATLAB that when this y is hitting 0, so remove this, so exclude these points. So so you can use the conditional statement that y should be greater than equal to 0. So by doing that, we can remove the extra point, or you can simulate up to the time up to which the projectile motion is being performed. So let me go to MATLAB. Okay, so today I mean, do coding in my inbuilt MATLAB. So yeah, or you can also do it in online also. So so ready to pen. Okay, so this is the code. If you remember, so this is the code which you have written in the last day for solving this damped oscillator using RK4 method. Yeah. So I will. So I mean, this is. I mean, so now this is the code which you can use. But what you have to do, so you have to just change the functions here. So let me copy it. So what should be the parameters? So I mean, you have dt, and then you have your time, which is the as the final time is written. Then what are the other parameters that you need to pass? So you have to specify what is the damping. So let me rename this as drag, and I will rename all the others omega with drag. So this is now drag, and then you have your gravity, which is okay. So the gravity should be 9.8. Let me take this value. and there is the stamping value, and there should be mass also. So mass. Okay, so let me take the mass to be 1, G 9.8. Then we have air drag. Let me take it to be 0.1, and also there should be an initial velocity. So, and also there should be the theta. So initial velocity I will call it v0, and assume. So let us assume, okay, 20. So 20, and what are the other things? Theta. So you have to specify what is the angle, which is 45 degree. So I mean, whenever you are writing sine theta, then you have to convert the degree to radian. And so if you want to convert the degree to radian, so I mean, you can do it with this formula. So pi by 180, and that will be multiplied with theta. So this will give you your radian, and this is the array where you will store. So let's take it 4, and what should so it should have 4 initial condition. So this is the displacement. So in the displacement be 0, and what should be this value? So it should be v0 multiply with, so what will be the uh, uh, velocity along x direction, initial velocity, into cos theta. So it should be cos radian, and then we have velocity, we have displacement in the y direction, which is 0, and then we have velocity in the y direction, which is basically v0 sine. So here we write sine. So this is, I mean, here what we are doing. So we are storing what are the initial values in the x array, and then here. So now we have to uh, change the function. So, and I mean, you want to pass on all the variables here. So and the order is important. So here let me just write down the variables that I want to pass in the function. So drag I want to. So what are the things that you need in your function? Okay. Okay, so you basically need G. Uh, G, you need K, M. So everything. I mean, almost everything you need. So let me pass every of the variables. Drag, mass, then gravity. then- So these are the things that you need to pass on. And what will be the first function? So this is basically Vx. So Vx is our just x2. So let me write down it. So x, and I will write here Vx, and y, which will be x3. So this is the, I mean, the third row. So and the first, so since the first one will be stored as y, so this is our displacement, and then we will have vy, which will be x4. And what is dx? So dx is basically vx, then we have dvx. So let me write down dvx, and dvx is minus k by mvx. So let me write down it. So here we have k, I mean drag, by m, and that will be multiplied with vx. And similarly, we have dy, and it will be dy. So let me just call it dy and dvy. So it will be dragged by m, and here we will have vy, and there will be another term in so gravity term in case of y. Let me look for it. So minus g. So we have to write down here minus gravity, and I will uh, so we have to write down here x because the so it is so first one is our position array of the in x direction. So this is our velocity in x direction. This is our then displacement in y direction. So which I will write just dy, and then okay, so dy, and then we have dv. So this is our velocity in y direction. In this way, so we have written down what the uh, we have written down what the function is. So let me just call it out projectile, and this is out projectile, and let me rename it like projectile damp. So this is the function name. Let me change all of them. And next drag in. So I have to pass on all the variables. So passing this. So here the arg4 method is calculated. So I mean it is evaluating the k1 value, what will then k2, k3, k4, and from that it is giving me what is the x value. So now what this will show us, so this will give us what will be the displacement along x-axis, and what will be the position in x direction, velocity in x direction. So similarly we can plot the others also. So this is tx3, which is position in y direction. I can just make it short and just y position. And this is x velocity. This is x position. And we have the last one, which is y velocity. So it will be 4, and here we have to write y velocity. Okay, so let me try to simulate. So because I have included time, I mean I haven't set any condition for time. So let me look at what is the output. So this will be lecture 6. Tile RP4. Okay, so there is some error in line 19. Okay, so here something is giving. Yeah, so if I look at it, style I need to change maybe because it is every style is same now. So let me just remove it from here and let us look at what it will be. Okay, so if I now okay, so if I look at the this will just remove them. Just keep it simple. Yeah. So y position you can see that it is going in the negative y direction. So that means time. So we have to put an condition so that I mean it execute up to that time. So how can you put how to put that condition? So let me try to do that. So let me decrease the time just to show you just to check that if the code is working fine or not. More or less time. Okay, so now what we will do? So we will check the elements. So here after this we are getting what is the y value. So let me look at the y value. So the displacement along y direction, and if I look at the array, so now you can see. So this is the initial y, and then it is increasing. Then it will come back to the ground after a certain time. So you can see that here it is going in the negative direction. So we have to filter out this. So how you can do that? So here for I equal to 1 of, so maybe length of t, because I mean this x has the same length of t. So because you can see that there is 41 and in t also there are 41 elements. So length of t. Now what is where it is stored? So y value is stored in the third row and all the column. So y3 all. So what it will it will check. I mean so y3 all minus 0, and you want this to be greater than 0. So the values of uh, x3 where it is satisfying. So you have to find this. So x, I mean x, and so okay, let me run. Let me check if it works in this way. So let me store it in another variable. So maybe it is giving the first element only. So let me try to get it. So, we have written down code. So linear interpolation, maybe in linear interpolation we have written down that. Okay, so how what you can do? So first we can store them. So let me do it. So first I will store all the values around third. So this is our this is our displacement in the y direction. So I will store in a y in a different array. So let me call it y disk. So this is our y disk, and we want to check for the whole length. So if whenever this y disk is greater than 0. So here I will write y disk minus 0 is greater than 0, and here I have to write y disk. So I will store it in a different array, actual y disk, and I will end it. So let me just write down this portion in a command window, and let me look at the output. So what is this x? So what is this y disk? So let me look at it, and okay, so I have to put here equal to 0 because it is omitting the first one. So if I put this condition, so now it will work, I guess. Okay. So this is our y displacement, as you can see from x. That so let me open the x. So this is our displacement in the y direction, and first we are storing it in a different array. Then what we are checking? We are checking for the elements where it is greater than 0. Then what we can do? So we can find the index of the last element. So for that, how we can proceed? So we can just write down what is the length of it. So this is the last element where it is 0. So let me look at in our X array for the 29th element, and that should be less than 0. Yes, you can see that here the y is now 0. So that means, so now what you have to do, you have to find what is the length of this actual y display. So up to that, you want to do the, you want to plot it, and up to that, it is the physical system. So after that, yeah, y negative means it is going to the ground. So what you can do, so you can find the index, which is length of this actual y display. So you can find the index here, and once you got the index, so you can plot it from 1 to index. Here also, so let me just plot everything from 1 to index. So let me replace the other ones. Fine. Okay, so now let me run it. Oh, so you have to, so now you have to change in the x also, t also. So here also you have to plot from 1 to index. So that is the, time you want to know. and if you want to know the what the time is, so for that you have to just write down what is the element, what is the value of t for that index. So it will give you the time, so it will give you the time of flight. So let me run it. So you can see that, so now, I mean, you can change the limit of this t. So let me make it, just make it look a little bit better. It's, so what should be the limit? So the initial value will be the first element, and the last one will be the index element, and that is 2.7. So I mean, we can change this GT. We can make this GT more. I mean, we can increase the number of data point to all to get this, to get the actual time of flight, because at this, I mean, so there are less number of data points. So that is why the point which is, I mean, greater than, so the last point is still 0.75. So I mean, you can, if you increase the resolution, then you will get point close to zero, and you can run it. Uh, T index, let me leave it here. Yeah, so now you can see that it is improved now, 2.75990. Now let us compute what will be the actual time of flight, and let us check if it is matching or not. So we know what is the formula. So basically, so let me try to solve the equation. So we have d dt. So we know that the time of flight is 2, if we recall correctly, 2v sin theta by g. So this is our time of flight. So let us calculate from the given value. So I mean, uh, and let us make the drag to be 0 for now, to check. I mean, if our code is giving the actual time of flight or not. So for drag 0, let me run it once, and let us look at t, which is 2.88. So I mean, yeah. So if, so this seems consistent, because if we don't have any drag, so I mean, there will be a less force in the y direction, so it will perform more. I mean, the time of flight should be more. So it is 2.886, and let me check the actual time of flight. So let me write here t actual, which will be 2 c 0, which is the initial velocity, and we have here sine theta. So it is just simply this one, sine radian divided by gravity. And let me look at the output. Okay, so this is 2.68862, and this is 2.886. Now if I mean, increase the resolution more, so maybe 0002, and now let me check what is the time of flight and actual time of flight. Maybe more increased resolution. And the more you increase the resolution, the more it takes the time, because then you will have, I mean, look at this X array now. Now it has this 20,000 data point in the execution. So I mean, it's a trade-off between your computational power. Trade-off between how much efficiency you want and how much computational power you can use. So but this result already seems the result that we are getting 2.886. So it is accurate up to third order. So it's almost pretty good result. So here what you can do. So you don't need up to 4. You don't need it. So you can just decrease it up to 3 and you can make it zero point 0.5. So that's how we can decide t. So we know what our system is and we know what up to where our system should simulate. So initially you try to find. So now what we are doing, initially we found a rough value up to which you can go. So up to maybe 2.88 is the desired value, 2.8862. So maybe, so that's why we are simulating it up to 3. So initially in the starting it was up to 50. So we have decided. So now we understand that we don't need to simulate the system up to 50. Up to 3 it is already good enough, and up to 2.9 also even. So you can go. So let me just pause it, stop, run it again. Okay, so now we can see that it's more accurate. So it's 2.861, 2.86, which is quite good. So this is the x position, y position. So now you can also find what is the maximum height it is reaching. So how you can do that? So for that, what you have to do, you have to just in this. So this is your y array, which is so so where is your y array? Yeah, actual y is. So this is your y array. So you can find what is the maximum value in it. So maximum height reached will be the max value of this actual y display. So you can run it and you will get what is the maximum height. So for now, let me just decrease dt to increase the to okay. So you can see that it is reaching height up to around 10.2041. So we can just uh, remove other plots. So let me comment it out. I just want to see what is the position in the y direction. That is good enough. Let me make it 005. Okay, so now this seems pretty good. Projectile motion kind of plot. So we are showing it from here. And so for example, now suppose you want to what you can do. So here you can use conditional. You can use iterative task. So maybe you want to run the value of this k. So the drag. So the drag. You want to start from 0 and you want to go up to 1, and you want to look at how this response is being changed. So how you can do that? So for that you have to you have to run an array for drag, and you have to do the task, this same task repetitively. So how you can do it? So since uh, so these parameters will be fixed, and the thing that you are changing is drag. So let me call it drag array, and maybe we will make it from 0 to in steps of maybe zero point 0.2 for initially and go up to 1. And this task I want to do repetitively for each of the array values. So the initial velocity, and these are independent of drag. So this you have to put out of the array, and if these things are independent of what is the drag value is. So that is why we will not put in the drag array loop. So here you will run a loop for drag. So drag value, it will take values from this drag array. So let me write a drag array, and this thing you want to do repetitively. So this is the end. So it will plot on figure one. Hold on. Okay. So display name. Let me display. Okay. And suppose you want to store. You want to store what is the maximum height reached for each of the drag value, and also uh, what is the t this time of flight for each of the drag value, and maybe you want to plot them also. So how you can do that? So you have to define array for that. So so uh, t array. So let me define an empty array, or this can be, so let me take it an empty array. Then you will have another array where you will store the maximum height. So max height array, and here you will store the maximum height. So now how you will proceed? So this is a t array and this is a max height array. So this is the value which you want to store. So how you will proceed? So t you will write down, you want to append this t value to the t array. So t array, this t value will be appended here. So here you will get the t array. Let me just uh, suppress the outputs here, and you will also append this maximum height reached also. So maximum height array will be equal to maximum height, and you will append this. Right. So here you are getting the maximum height. So let me remove it. Let me comment it out, because this will be not the actual formula if you have drag. So you will have you will have dependence on drag also. So once you done with this array, so after that you will get what will be the array. So maximum height array. If you want to print it, you can show it. You can see it here. Then or you will have t array also. So let me run this now, because you can see that this is the maximum height. So the maximum height is changing with increasing drag, and also the time of flight is also changing with changing drag. So we can create so you can plot them also. So let us plot it. So figure 2. So first you will plot in x-axis, you will have the array which is your drag array. So you will have your drag array here, and you will have your max height array. So first, so let us take the t array. Then in the same plot, if you want to plot the maximum height also, or you can plot it in different figures. So let me just initially put it in a different figure, because so this height, the scale are different. So it is 10, this is 2. And also if you want to visualize two data, two plot, two in the same figure which has order of magnitude different in the y scale, then you can use the log scale also. But just for now, let me proceed with the, let me go to a different figure, figure 3. So the hold on will now will not be needed, and here you will plot the max height array. This max inside array. So let me run it now, and I'll just suppress this output. Okay, so let me give the names like X level is time, then we have Y level which will be uh, time of light, and similarly here also you can put level. This is time, and in y-axis we have maximum height reached. Then you can, I mean, put options like line with maybe two, and you can put also title. So title. Okay, so this is not time. So x-axis are drag, and title maybe you want to put something like dependency with time of flight with drag, and you can put some similar title here if you want. So this will be maximum height with drag, and here maybe, so what will be the display name? So maybe, I mean, printf, a printf or some function can you can use. So I will check. So let me just run it first. Okay, so this is how maximum height is being changed with the drag, and here also this is how time of flight is changed with drag. And I mean, so this is a projectile motion. So this is how, I mean, you can gen so you can play around. So I mean, instead of drag, so you can check with different kind of with different mass. So I mean, if you make the drag zero, then I mean, if you change the mass, that should not affect the, I mean, uh, so the time of flight. And I mean, so you can check if there is any dependence. So for example, you don't know what is the solution. So with this code, you can explain the dependency. You can explore the dependency on parameter. So for example, now you want to check. So I mean here, what you want to, so you can do a 3D plot. So I mean you can plot the time of. So I mean you can plot the position and velocity in x direction. I mean, or position in the x direction and position in y direction, which will be trajectory. And in the z axis, you can put another. I mean, you can do plot. So you can do line plot in 3D. So we have learned about how to do the line plot in 3D. So for simplicity, let me just take the drag to be 0, and let me just okay. So these plots, I mean, are irrelevant now. So let me comment it out. Okay, so let me comment it out here. Okay, and this is for one drag value. So let me run it. Okay, so this is computing for only drag 0. So this is the projectile motion. This is x and t. Suppose instead of x and t, you want to plot. So let me copy it, comment it out, and so let me get another figure for this. So I will put legend. So this keep it here projectile motion with their resistance. mm, you can write it on a 3D trajectory, and here you can plot x. So you can just you can so this is our y displacement. So here you want to have the x displacement. So for that you have to put here 1. So this will take you this will plot the all the column values for row value 1. So which is our displacement in the x direction. So I mean, let me just remove this display name for now. The legend command. I mean, just comment it out. So x level, this is our x, and this is our y. So let me run it. Okay, so I mean, I have to put this. What is this plotting? Okay, so initially it is also plotting it. So I have to put rename it to figure 2 and let me run it. Okay, so now it is almost okay. So this is 1 and this is 3. So in the x-axis we have the displacement along x direction, and in the y-axis we have displacement along y direction. So yeah, okay, it is fine. And what we can do, we can I mean to put the limit. So x limit, what should be the limit? So the in the x direction, the first value should be x 1 1, and the last value should be x 1 index. So and let me run it. Okay, so this is I mean this is our x displacement, this is our y displacement, and this is how it looks in 2D. So this is for a fixed time. I mean, so now suppose I want to look at what is this x, how these x values are changing as a function of time also. So I have to put here plot 3, and here I have to put the z axis, which is basically t, and which will run from 1 to index. So let me run it. Okay, so in this axis we have the time value. So with time, so you can see that this is how the x and y value, they're evolving as a function of time. So in this way you can visualize it in 3 dimension also. So this is your x, y, and time. So you can I mean look from multiple angle. So I mean from top, if you look at it, so this is how it looks in 2D. Now I mean, but so the time is also an function. So with time it is also increasing. So you can see that x is changing with time. So y is I mean also, so in this is the y direction. So this is how y is evolving as a function of time, and this is how x is evolving as a function of time. So we can in this way you can visualize in the 3D plot here. So 3D line. So I mean, you can try to play with different kinds of parameters. So you can check for different kind of values of m. You can check for different kinds of values of v. How the things are changing for different theta. You can check and so on. So I mean, you can create different loops. So I mean, in the same code, I mean, you can create multiple loops. So for example, you want to create a 2D, I mean, a surface plot where I mean you will have two independent. So I mean you want to check for a range of drag value, you want to check for a range of mass value, and for that you want to have a 2D plot of the maximum height list. So how you can do that? So I mean, that also you can try. So I mean, there are a lot of things to explore with this kinds of problem, and it shows you, I mean, how you can play with the system. So if you even if you don't have any rigorous knowledge about how you will solve this differential equation, how you can, I mean, so there can be, instead of simple function, there can be complex things also. So if you don't have any I mean, idea analytically how to solve it, but by using this numerical integration method, and I mean, with using the tools that you have learned, so array and so on, so you can visualize and you can play around with system, and you can infer to some degrees, infer up to some degrees about the system. So for example, from this code it is evident that if we have I mean, uh, if you have a larger damping, then the time of flight will be reduced, and if we have, I mean, larger damping, then also the maximum height, that is also being reduced, and it also, we can also plot it. So, and after, once you learn how to fit a data, so you can try to fit also different kinds of functions. So maybe you can try to fit an exponential decay to the curves that you're getting, and if it is fitting well, then okay, then you will have idea that the the height, maximum height that is reaching, so that is falling exponentially with time. So in this way, you can play around. You can play with the system. You can take a differential equation. You can try to explore the system. I mean, using this simple tools. Okay, so now we will take a quick 2-3 minutes break, and then we will proceed with our next problem. So we will start after 2-3 minutes. Okay, so now we will learn about how to do the fitting in curve fitting in MATLAB. So I mean, as you have seen in this example also, so if you know how to do the curve fitting, then you can try to, in MATLAB we can try to fit the, I mean, so the graph of the maximum height with that. So you can try to fit with the function. So maybe, I mean, by looking at the graph, so maybe it seems like, so there is some exponential dependence. So let me just pull out that again. So let me take larger values. And let me just, so plot it. Mm, just, so keep it if I want. And now let me count it out. And okay, so I have commented out the plot itself. Okay, so this is the maximum height with drag, and this is the time of flight. So it seems like that there is an exponential dependence. So suppose you want to know, I mean, if it fits with the exponential data or not. So I mean, if you know how to do the curve fitting toolbox, then you can I mean try to fit with it. So for fitting any curve or any data or any graph like this, so there is an inbuilt toolbox in MATLAB which is known as curve fitting toolbox. So to call that, you have to write CF tool. So as you can see here, the CF tool, and you have to run it. So once you run it, you can see that it is very busy. So it will open a pop-up window where, so you can see the window called curve fitter. So this has opened, and here what you have to do, so I mean you can see here a lot of things have opened up. So first you have to select the data which you want to fit. So what you want to fit, we want to fit for example, suppose this, so maximum height with drag. So what is your x for this? So your x array is your drag value, if the drag array is your x, and what is the y axis, it is the maximum height array. So you have to select the data first. So here you can see there is a select data option. So you have to click on this. So you will see that this will, after clicking, so you have to do the left click. So after left clicking, you will, this will open up. So in X data, you have to select what is your data. So these are the variables that are stored right now. So it will show what are the variables stored. So in X, you have the drag array. So this is your X data. So and then you have to select your Y array. So what is your Y data point here? So your Y data point is maximum height. So here the graph will show. So this is the graph that you are getting. So this is I mean and then you can close it. So you have select the data, and I mean MATLAB, I mean it, whenever you open it, so it always generally fit a I mean polynomial or degree on. So it's basically linear function. So then you have to select the function with which you want to fit. So you can fit a polynomial. You can I mean change the degree. So for example degree 3. So I mean, and here by clicking this, you can uh, see that there is a lot of functions. So there is this exponential. So I mean, maybe you can try to fit it with exponential, and there are advanced option also. So I mean, there is algorithm. You can, this one is good for fitting. So this so Levenberg method, and you can I mean uh, check with different kinds of I mean and here you have to select what are the coefficients of fitting. So I mean this is your equation a e to the power bx, and what is the value of a starting value and what is the value of b that you have to select. And after select, so it will fit and it will show you. So the results will be shown here. What is the a value and what is the b value, and it will show you the r square. So for good fit, I mean it will be like 0.98 point, it will reach around that value. So that will be a good fit. So you can see that it is not properly well fitting with an exponential. So you can try to write down your own function. So what function you can write? So you can go to the custom. So you can, and you have to click on that. So when you click on the custom fitting, so here you will see and the equation that it is using. So you can try to. So this is the equation which is fitting, which is being fitted now, and you can see that r square is I mean almost good enough. So instead of this, maybe you can try to fit two different. So you can write your own function. I mean you can change it. So maybe here C D, and the fitting is not good now. So maybe, so this is not a I mean so the data that you are getting, it is not fitting with this model. So you can play with different kinds of fitting function. I mean you can have an intuition what you should uh, what what is the fitting function you should take. and with that you can try to play. So maybe a plus bx. So how is the fitting now? So chi-square is 9.987. So I mean, so these are the model which you can take. So you can play around with this fitting function. So maybe so this function seems to be quite a good fitting. So now let us explore this custom function more. So yes, and also you can create. I mean, export the. So once this is well fitted, so let me just to the custom function. Let me just remove this because without this also the data seems to be quite well fit. So the initial value is not fitting well. So I mean the function would be different from this. So let me show you with a known example which you already know. So this is the so I mean if you want to get the code for it, so I mean then you have to click on export and you have to so you can export this figure, and here also you can have the residual plot also. So residual plot just basically gives you what is the difference between the actual data that you have in your system that you have in your graph and the the point that you will get from the fitting function. So the blue curve is the fitting function, and at that point, this will be your value corresponding to the fitting function. So the difference between the actual data point and the fitted data point, it gives you the residual. So this is a residual plot. So it shows you how your fitting function is deviating from your actual data. So so you can export this figure if you want. So I mean, so and this you can save in your system so that if so in MATLAB, so here you can save as a MATLAB figure, you can save it as a PNG file or PDF also. So I mean, all of these are available. So this is and also you can export the code also. So I mean, you can generate the MATLAB code for this fitting. So this kind of fitting function that you have done. So if you tell MATLAB to export the code, so it will give you the code to for the fitting. So generate code, and here you can see that the code has been generated. So this is the code. So I mean, if so after what is the advantage of this generating code? So you can save it as a script here, and I mean you can call this fitting function to any other problem also. So I mean suppose you are working with a different problem and you want to quick. So whenever you are defining custom function, so I mean if you want to use the same function for a different problem, and so you can just call this function, so it will give you what is the fitted result also. So it will show you the figure. It will show you what is the actual data or what is the data that you are giving and what is the fitting function that you are getting. So that is the so that is the advantage of doing the fitting in MATLAB. So once you know what is your custom function, so that function. So with that function, you can create the MATLAB code, and that you can use for analyzing data for any. Analyzing data for different problems. So, for example, suppose you are working with the problem. Suppose with electric field, I mean you have charge, and you are getting some. I mean maybe electric field value as a function of displacement as a function of distance, and maybe you want to check if that fits with the fitting function that you are creating there. So you can just call this function there. So if you call it there, So it will check if it is a good fit or not. So it will give you the output. So what is the chi square, what is the r square value, what is the goodness of fit, and so on. So in that way, you can play around with the fitting function. And let me show you with known I mean problem. So maybe damped harmonic oscillator. So what is the solution for a damped harmonic oscillator? So let me start with the solution only. So let me clear everything first. Okay, so for example, you're creating an array of x, and for this x, you are having a solution. So for example, a and y is a sine 2 pi. Okay, so let me call it t a. Then you have frequency, which let's say 1, a is 2, and this is your y array, which will give you the x value. So let me run it, and save it as lecture 6. Okay, so this is your t array, which is running from 1 to 10, and from that you are getting the y value. Now if I want to plot it, so I will just write plot t is your x-axis, then in y you have dependent parameter. So this is how your system is working. So now if you want to add damping to the system, so let the damping be, let us take the what the damping is. So here you can exponential, you can write on this exponential. So for example, damp. So this is the damping factor, and we have to define what damp is. So let us make it point 1 and look at the output. So we have to use here multiplication sign. Let me run it. Okay, so it is greater than 0, so that's why it is increasing. So maybe exponential for decay you have to less than 0. Okay. So this is how your solution will look like, and let us try to increase the number of data sets, because then it will look more smooth. Okay, so this is how your system will evolve. So let us just put the selection. So what will be, so t first will be our initial, and t end will be our last value. Okay, so this is how your response will look like. Now, I mean, so for example, you have a system. You are doing an experiment where your system can be modeled as a damped harmonic oscillator. But since you are doing experiments, so then it will not be a perfectly so perfect sinusoidal perfect response like this. So there will be, due to the presence of thermal noise, so there can be some fluctuation. So we can try to simulate that by using the rand function. So you can use a random, we can add a random number to each of the elements. So how we can do that? So we can let me call it y experiment, which is the exactly which is the from the model, and with that we want to add some random number. So let me add random numbers between 0.1 to 0.3, and what will be the row value? So y, and so each row value should be 1, and what should be the column value? So column value, it should be the length of y, because for with each element of y, I will add a random number. So, and which will lie between 0.1 to 0.3. So here we have to write length. So we can try, if we run it, we will get y experiment. Some error. So let me check the output here first. Okay, so you have to give here integer value. So let me try to do that. So maybe here I have length of y. We run it. Yeah. So y experiment, you will have values. Uh, so okay, so maybe here I can multiply with zero point 0.1. So let me run it. So this is your y array, which is 0.1135, and let us look at y experiment. So this is how, I mean, okay, so maybe we can make it more smaller fluctuations. And let me just plot it. I mean, so hold on, and then we can plot t and yx. So let me run it. So maybe change the damping, and here I will just incorporate a style. So maybe like this. And here something like this. Because incorporate this. Let me run it. Try to change this. Okay, so I have to put the close all because it is just updating in the same figure. So close all, clear all. So these are the things which I need to put. Okay, and you can try to plot the data also, what the actual data will look like. This number of data points. Just the minus works. Yeah. Okay, so yeah. So for example, in experiment, I mean, you will not get this kind of simple graph. So I mean, ideal things you will not get. So you have system in presence of thermal noise. So I mean, the stochastic noise present. So you will get something close to this, like the red curve. So it will not exactly follow sinusoidal, and I mean, you will get this kind of point. So now suppose you want to. So now suppose you don't have. Now let us try to fit this data and let us try to extract what is this A value, what is the damping value, and what is the frequency value. So for fitting, so what you have to do, you have to call the CF tool. So already opening. So now you have to go to select data. Let me close it. So let's go to this is for the previous one. Okay, so first you have to select your data. So you have to select your X data, which is T. Then okay, so let me just first increase the data point. Toolbox, minimize it. So maybe 0.02, so that will increase the number of data points. So now we can call CF tool. Let us select the data. The x-axis is the street data and y-axis is your y experiment data. So if I okay, so the T has been uh, uploaded on the previous session. So let me just close it and run a new session. Okay, so select data. So this is our x, which is T. Then we'll go to y data, which will be our y experiment. Okay, so these are the data points. And if you select y here, then you will not, I mean, yeah, you can see a smooth data points. But if you select y experiment, I mean, you will, in experiment you will have similar, I mean, somewhat this kind of data. Okay, so you are done with the data. Now let us try to look at the function which you want to fit. So I mean, there are this inbuilt. So you can try to look at other things if there is any function present like that. So generally, this damped oscillator system function is not present. So you can go and write custom equation. So and what you can do, so you can just copy paste the equation. So this is the thing that you want to fit with this function. So this is your model equation. So let me put it here. Okay, so t is your basically x. Here you have to write independent parameter as x. So this is your x, and this is how. Okay, okay. So these are the, I mean, initial values which it will check, and this is, I mean, how the fit will look like. So these are the fit options. So let us go to advanced option, and what are they? So here you can change it to this. So and in the custom, so this is the equation, and on the in the fit option, you can go to the advanced, and here you can select the starting values. So a starting point, because it's around 2, so maybe you can try to give it 2.5 or something, and you can try to check the fitting, so if it is fitting well or not. And this is, I mean, maybe 1.1. And damped, you can, I mean, so this is negative, so let us make it minus -0.2. Yeah, so I mean, so these are the things that you have to, I mean, you have to have a little bit idea about system. So since this is damping, so you cannot have this damp coefficient to be positive, so that is why there is this problem. So once you make it, I mean, so you have to give a good starting point. So maybe even if I, so let me try with 25. Suppose I don't have any idea that it should be around So it is fitting till now. Okay, so you can see that it is fitting well. So this frequency I can give it 10. Okay, so it is not a good fit. Then you can play with it. You can try to make it 5 and try to look how the system is responding. So you can track the R square value. So if I mean okay, so maybe a little bit better. So you can try to change so in this direction. So maybe 3, and you can try to look at the system response. And now you can try to make it 2, and in this way I mean you can give the initial starting point of the parameters, and it will fit for you. So maybe 1.1. Okay. So you can see that this is the starting point, and this I mean so you can also define what is the lower limit of the fitting coefficient that you will go, or the upper limit also. So once it fits, so you can go to the result section, and it will give you the values. So this is the value that it is accepted. A is 2.03. I mean we have started with 23, but from fitting it has extracted this A value to be 2.03, the damping to be minus 1.01 minus 0.1038, and F to be 1. So let us go back to our so we can export this, and I mean, we can also look at the residual plot. So this is how the residual plot is look like, and we can also export we can also generate the code for this fitting. So you can generate. So once you have clicked exported, so maybe yeah. So here you can see that this is the how the so this is the function for this for this damped fitting, and you can see that A is 2, F is 1, and damping is minus 0.1. But so there is this little deviation from due to fitting, but you so it will not exactly give you this value, because you have thermal noise present in your data, I mean random numbers present, and also I mean you cannot fit your data 100%. So it's not 100% fitting. So due to this random number, so it's give you I mean the best fit. So basically, it is calculating what is the standard deviation from each of the point. So this is your data point, and from the fitting function, it is calculating the standard deviation of each of the data point. And so the way of fitting is I mean it tries to minimize the sum of the standard deviation. So by minimizing the sum of standard deviation, it will give you the line of best fit. So by from this line, it will calculate what it will use this model, and it will calculate what is this damping value if and if. So in this way, you can I mean play around with the CF toolbox. So you can I mean you can create your own custom function for fitting. You can fit it, and you can generate a code so that you can use the code later. Okay, so that is it for today's video. So I mean today we have learned about I mean how to so we have taken a simple problem which we have known. I mean the problem of projectile motion, and then I've shown you the power of MATLAB. I mean MATLAB, how we can how simply I mean not MATLAB, so any programming language. So how you can take a simple I mean you can take a simple equation or even complex equation, and you can try to infer the dynamics of the system. So how I mean dependence of the system on some parameters, and try to infer some how we can in how we can input physical conditions to your model, and how you can check the I mean dependency parameter, and how you can visualize it. So you can feed a function also to it, and and also extract the meaningful parameters out of it. And then we have also looked at how to fit a function and so on. So in the next lecture, we will learn about how to do the Fourier transform of this. Next lecture, we will go into fully into this harmonic oscillator system. So we will look at FFT, how to look at the Fourier response of the system, how to look at the Fourier domain, and how we can look at the phase space. Then we will explore the nonlinear, I mean damping oscillator, and so on. Okay, so that is it for today. So I'll see you in